Right, good afternoon everyone and welcome to SMI's lunchtime webinar. It's fantastic to see you all again. Today's presentation is from Associate Professor Mohsen Yahyaei. He's Group Leader of the Advanced Process Prediction and Control, or APCO Group, at JKMRC. Mohsen began his career at a coal washing plant in Iran. He completed his PhD in 2010 and has been with JKMRC since 2011. As leader of the OPCO program, his aim is to transform unit process modeling and simulation to develop and apply new techniques that make greater use of data generated on sites and sensor technologies in combination with advanced process control, computational analytics, and modeling techniques. Today is presenting on the potential improvements can be realized by actively involving plant metallurgists and plant managers in designing and evaluating different levels of process control systems. As ever, there's an opportunity for questions and answers, Q&A after the presentation. You'll see at the bottom of your screen, there is a button where you can submit your questions online. Please feel free to do that in any stage during the talk. As a question comes up, please post it. And at the end, I'll read through the questions to Mohsen and we'll answer our way through it. So I'll hand over to Mohsen now. Thank you very much.
Thank you very much, Navid, for the introduction. And good day, everyone. I hope that you can see the slides and you can hear me very clear. So before I jump into the presentation, I would like to acknowledge my colleague, Francisco, who contributed to this presentation as well. So I took the honor of presenting the work, but he had a contribution, as well as the rest of the APCO team that actually helped me with preparing the webinar. Today, essentially, what I'm going to discuss is go into some of the basics of the process control to review for people, especially that they are not very familiar with the process control as well. And I will touch on why us as metallurgists have to be involved and we should know about process control as well, why it is important. And then I wanted to share some of the experiences that I had in regard to application of process control in mineral processing and what are the things that actually usually goes wrong. And then I would like to basically grab your attention to what the process control course that we have developed, and we are offering that course in August 2020, which is a 4-day course reviewing from basics to what the advanced aspects. And then, as Neville mentioned, we're going to basically have a Q&A time. So hopefully we can answer some of your questions as well. So in regard to the process control, I think there's no doubt actually why we need process control, but there are lots of different perceptions. Depending on who you talk to, they might see different duties for the process control. I basically grouped them in 3 different groups. Essentially looking after the safety aspects of the process, either looking into equipment or people safety. And that's primarily by controlling a level of material in sumps, bins, checking temperature, pressure of different things, and also looking after the operating limits of equipment. Also, the another aspect would be around environmental standards and protecting the environment. So by optimizing the operation and trying to reduce the emissions, preventing spillages, and etc., and other stuff. And I think another aspect which often is less paid attention to is the plant performance targets, and that's essentially achieving the productivity. So although we are designing the process control and trying to use them to achieve those process performance, but often because we are paying more attention to the safety and environmental aspects, we might actually underlook the operation part. And I think that actually that's one of the key aspects that why the process people have to be involved as well. That while we are looking after the safety and environmental aspects, we can actually come up with some novel ideas in terms of how we can design the control for the process control. But essentially, these are the 3 aspects that the process control have to fulfill to fill the purpose of that work. And why it is important. So I think as we know, the variability in the process actually it costs, and that comes with the issue of you have to run your process in a conservative mode. As I presented in this graph, essentially, if you don't have any control over your processing plan, so if you're looking at the plant throughput, you're going to run all over the places, and you got a large variance in your throughput. And that means that actually to avoid any issues in your operation and basically preventing the process to go over the operation limits, you have to run it at the conservative set points. Whereas if you have a process control and you use it to stabilize the process, because now you're narrowing down your operation, you reduce the chance of going over the board. And that means that actually in many aspects, you would be able to push even the average and run it at higher average value as well, which means that actually increase the performance while you're maintaining the operation within the constraints. So, and that's a key role of the process control, especially at the stabilizing stage, which means that actually you reduce the variability of the process, and that helps you to push the boundaries and run at as close as possible to the operation constraint. And why us as metallurgists should care about process control? I think I was thinking essentially if I want to discuss that with metallurgists, I would group them into two aspects. One of them is at the design stage, specifically looking into the control logic, as I briefly mentioned at the beginning as well. So we want to look into the process control logic in terms of the process performance as well. So while we are looking after the safety and the environmental aspects, we want to make sure that actually we design the control logic in a way that actually caters for the process needs as well. And that's the key point. When you involve metallurgists that they have a good understanding of the process, they can actually guide the control logic to look after the process needs and take care of the constraints that the process has. And also it's going to help the metallurgists to understand the capabilities that exist within the process control and use that to the benefit of optimizing the process. And another thing is going to give us the common language that we can use it to when we talk with the process control engineers and when we're talking about the designs and the needs of the process. And in many cases, we have been on sites that actually the metallurgists have a close relationship with the process control engineers. That's the place actually I saw the process control works the most efficient way, because they can communicate in a common language and they can express the needs very well. And because they're aware of the constraints that exist within the process control, they can actually come up with a more realistic needs and more realistic way of application of the process control. The other aspect is essentially when you're trying to diagnose a process. And I think having a good understanding of the process control is going to help you to identify if any issues that you face in your process when it's running, whether it comes from the process control, and you can do the preliminary diagnosis and identify where exactly is the issue. And because now you have a common language as well, you would be able to communicate that issue properly with the control engineers to try to resolve that as well. And again, that's another aspect that I found often it's very hard when you don't have a proper understanding of what's happening in the control space. And often I found that actually some of the problem from the processing side had been attributed wrongly to process control and vice versa as well. And I think having a good understanding of the basics of the process control, in particular with the applied sense, is going to help us a lot to improve that aspect. And essentially what we have been looking at was trying to design a kind of a refresher course, which is more practical as well for process metallurgists, that actually helps them to refresh the basic concepts of the process control, because as far as we know, in many cases, the process, the chemical engineers or process engineers that have been educated in universities, they have done some level of process control courses, but often that has been done by electrical engineers. and the key point in this course is trying to match those understanding with the metallurgy side as well. And that is going to help us to benefit from the advantages that I mentioned in this slide. So let's go back into some of the basics. So how the process control works, as I mentioned, the main objective, especially at the lower level or the stabilizing level that we're talking, is about stabilizing the process. And that can look into different aspects. So either it's the input material and they're trying to stabilize those. So like, for instance, in many of the operating plant, trying to stabilize the plant throughput, water addition to different processing units, or chemical additions to flotation or leaching or dewatering process. Also, you're using the process control to stabilize the equipment operation, whether it's the power draw of the equipment, speed of running different things, the person solid, like pressure in different units. So those are basically which related to the equipment itself. So you will see that actually there are lots of stabilizing loops that actually has been used in that aspect. And then in many cases, monitoring and controlling the equipment operating conditions, which is like level of material inside an unit or equipment, checking the load, the temperature, like cyclones, when you're running cyclones, looking into the pressure of those, and many other variables. So these are essentially the targets for the process control. And if you look into a processing plant, you will find that actually there are many stabilizing loops that they are running in the background to trying to control different aspects of the project, the process. And the main objective is, as I said, is to achieve the safety and the environmental as well as performance objectives that is set for the process. So let's look into a basic process control loop. This is kind of an overall structure for a feedback control loop. So if you're talking with the control engineer, generally they talk about feedback loop. And as you can see, it's actually a closed loop. Essentially, the loop starts with the process here, which has some inputs and some outputs. And out of those outputs, there might be some of them that actually it's your interest for controlling, and they call them control variables. There are some factors that actually is affecting your process performance, which you might not have great control on those ones, or you cannot change them. So we call them disturbances. And there are some factors that actually they affect your process and you might control them, which we call them manipulated variables. So essentially the way the loop is working is you get a measure of your control variable using a sensor or a measurement technique, and then use that measured value and check it against your desired value that we call it a set point. And then based on the difference between your desired value and your measured value, there would be an error, which would be the input to your controller. And again, in a controller, we have a variety of different controllers that we use. The most common one is a PID controller, which stands for proportional, integral, and derivative controller, which is the most common one. And that PID controller or any other type that you're using is going to create an output based on the error, which is the input to the controller. And that output essentially is going to activate your actuator, which in turn is going to change your manipulated variable in a way that actually tries to push the output toward the desired value. And this loop is basically going to be iterative process that actually you measure the parameter, you check the measured value, check it against the set point, and based on the error, you take a control action and manipulate the variable. And you go on up to the point that actually you can reduce the error to a certain value and you stabilize the process. So if I want to give you an example that actually is kind of a everyday example and makes sense to most of the people, I think I can use a car as an example. So let's assume that you are driving your car, or you put it into basically cruise control and you want to drive your car at a certain speed. So what happens is you measure your speed of your car as your control variable. There are lots of other parameters that they act as a disturbance that you don't have control, like the condition of the weather, the road condition, the traffic, and all of those. And the gas rate is the parameter that you can use to control the speed of your car. So based on what you measure using your speedometer and your desired speed, so either the driver or the cruise control is going to basically use that difference to adjust the gas pedal. And that gas pedal adjustment is going to basically feed to the engine and changes the gas rate to adjust the car speed. So this is an example of closed loop that actually you're using. And the brain or the controller in here is a cruise controller or basically the human brain that is basically driving the car. And that's an example of a control loop. But there would be some occasions that actually this closed loop becomes an open loop. And when you have an open loop, it means that actually essentially you don't have any control. So the control, it's broken at some point and the whole loop is not working. And that means that actually you're not controlling the car. So in this example, for instance, one of the key points was like, you're trying to achieve a certain speed. And if your car is too old and you cannot get to that point, so if you hit the limit into your gas pedal and you're pushing the gas pedal to the maximum limit, essentially you want to go higher speed, but you are already at the maximum gas pedal. So essentially the engine cannot change the gas rate anymore, which means that you cannot adjust the speed and get at higher velocities, speeds. And that means that actually, although the whole loop is working, but because the gas pedal hit the limit, you can't control the process. And that becomes an open loop essentially. And there are several other factors as well, like if the controller is not on, or if there's something wrong with the gas rate, or if something wrong with your measurement, all of that can cause to change an open loop into a closed loop. Now let's look into one example that is more familiar to the metallurgists. So let's look into the froth height control in column flotation. So in column flotation, actually, we have many of the loops that actually working around the column flotation to try to control it. And this is one of my favorite topics because I've been involved in my master's degree to design and develop one of these ones. That's why I'm using this example. But one of the key loops that normally people are trying to control is the froth height in column flotation. And my colleagues that actually they're working flotation, they know that actually has a significant effect in performance of the flotation. So generally in column flotation, they use pressure transducers to measure which one is normally in a froth zone and one in a pulp zone. And they use the pressure difference to calculate the froth height. And those calculations are actually done in DCS. And then what we do is normally we use the set point for the froth height and then feed it to the controller, which controls the tail by adjusting the amount of tail coming out of the flotation column, we can actually manipulate the froth height. So if I want to translate this into a control loop, feedback loop, that's how it looks like. So essentially, you have your column flotation here as a process. The pump speed, which is the tail pump, is your manipulated variable. And you got feed flow rate, air flow rate, and lots of other parameters that actually is going to affect your froth height as well, which normally you don't control them as much. And then you use your pressure transducer as your sensor to measure the froth height. And then using the current froth height and checking against the desired froth height, you can use the control package or your DCS to calculate what's the desired pump speed. And that desired pump speed is going to basically transfer into the variable speed drive, which in turn is going to control the pump speed and try to manipulate the froth height. So that's one example in your basically stabilizing the froth height in a column flotation. In our course, actually, we're going to go into different loops that is in action in different part of the process. That's what basically we're going to cover in the course, and essentially looking into different control strategies. What are the normal sensors, usual sensors that people are using? What are the pros and cons of different sensors? And essentially looking into different controlling techniques and lots of common issues that normally we observe in processing plant. So that's essentially our key objective when we go through the course. but I brought one of these as an example in here. So the focus in my slide at the moment would be mainly around the stabilizing control, which you can see it in here. But we know that actually there are other levels of control which nowadays are more common, and basically most of the operations and people are talking about them. And if you want to explain those ones, so another level of control that you can add to the system is the supervisory control, which means that actually you can use models that can run in parallel to your stabilizing control and use the processing details as well as process constraint to start calculating a desired set points for your stabilizing control. So essentially, instead of operators trying to take over for setting up the set points or interlock loops to setting up the set points for those control loops, we try to use our models to find what would be the best set point for the process, and we use that, which basically we call them supervisory control, and the underlying tools that we use is basically model predictive control. A higher level of control is optimizing control, which again, you will be hearing this one many times in different meetings and promotional things, especially around digitization. And that essentially is linking your process control into a broader process chain and trying to incorporate the limitations of the whole value chain into decision making for how you run your stabilizing control as well. But the key point in here is essentially the stabilizing control is the fundamental part or the foundation base before you move into supervisory optimizing control. And that's why we decided to run this first webinar focusing on the stabilizing control. But in our 4-day course, essentially, we are looking into the supervisory and optimizing control as well. And we are planning to run another webinar which focuses in those two later in the time as well. So let's look into a few aspects of process control in neural processing. So I think the first thing you should notice is there is a huge advancement in what's happening in process control nowadays. So I put one view of the old kind of process control rooms and the new ones that this is like a BHP integrated remote operation center in Perth. And you can see it's a huge difference now. And that's because of the advantage of digitization and advances in the technology, which help us to improve a lot. And the key point that you can see here is having lots of cameras, a visual observation of the process, which basically is a key point. And if I want to look at the spectrum that is available at the moment in terms of the control, so in the past, there was a lot of operations that actually they've been running manually or in a local mode, but nowadays more and more they are running in distributed control centers and essentially running the stabilizing control. And now the balance is more toward the advanced control and model predictive control. And there are lots of operations that are actually moving toward that direction. But believe it or not, I've been in operations that still they are running in manual mode or local control. There exist still, but majority of the operations, they at least they got the PID controller and they are moving toward advanced control. And again, that's the part that actually we are seeing. It's important to focus to have a better understanding of what's involved in advanced process control and what can be done. And as I mentioned earlier, we shouldn't forget about the role of the PID controller and the stabilizing controller as a fundamental part, which is important as well. So just focusing on a couple of common issues, which we observe normally when we go to the operating plants. So this one is a simple crusher process and some of the control loops around the crusher plant. Generally, we control the power draw of the crusher, and in many cases, the bin level is important as well, especially around the safety aspect, and also the overfilling of the crushing chamber. So these are the typical things that actually the control logic normally take care around the crusher plant. But in many cases, what we see is inappropriate setup for the control objectives, in many cases I've been in operations that the focus of the plant is controlling the level in the bin rather than controlling the power draw of the mill, the crusher. And in many cases, that means that actually you add fluctuation to the crusher for the sake of stabilizing the bin level. And that basically needs revisiting the logic. Because these plants are working in a very harsh and dusty environment, generally the sensors, the maintenance of the sensors are other common issues that we face. And also saturation of the final control element, especially around the feeders and set of the feeders. We found lots of issues around that. And in our course, we focus for each process units, we are focusing on what are the best practice in different control logics and how we can adopt the control logic at different operations, and also focusing on different sensors, the pros and cons of different sensors, and normally how you can do the maintenance and how you can do the diagnosis as well. And if you go into the whole process, another level of complexity is going to be added. So the previous one is essentially looking into one unit, and you see there are lots of stuff in here happening. But when you put it into a concept of the whole flow sheet, there will be lots of aspects that actually is going to interact in here. So the interlock between different loops, the variation in performance of different units, these are going to cause lots of issues as well. And that's another aspect that actually it needs to be covered as well. In a typical grinding process, normally you will see that the SAG mills or mills, they're looking into the power and load of the mill and they're trying to control that. With cyclones, generally the pressure is another aspect that they look into that. Again, in many cases, inappropriate control objectives are the key point, especially in the units that they are interacting with each other. When you set the objectives wrong, it means that actually you might underload one unit and overload another unit. And that's a common issue that we see. And in many cases, actually, people, they attribute it to essentially to the process, but in reality is a control aspect. So here come up, these are some of the examples, like the feed rate. This is a particular site that I've been looking into that. And the tuning of the feeder had an issue. And essentially in 170 ton per hour feed, there was a fluctuation of plus minus 70 ton per hour, which basically introduces a huge surge to the process. And that can be resolved by tuning. The positioning of the sensors is another aspect and the wrong logic. Like especially the flow meters, in many cases, I've seen cases that actually they set up flow meters in the places that actually the pipe is not completely full, so you get the wrong measurement. You have a sensor there, it's working, but the measurement is wrong because of the wrong installation. And we cover those aspects again in our course in all of the processings as well. Wrong control logic, especially with the cyclones, is a very common one. So you can see how the operation of a cyclone fluctuates over the time. And that's simply because the control objective here is to set up the sump level and trying to stabilize the sump level. And that is by sacrificing the stability of the cyclone pressure. And we cover a lot of these type of aspects throughout the process in our course. Complexity of the process and delays is another aspect as well. So we are dealing more and more with different, with the complex process units. As I pointed in this slide, so you might have your feeders and measurements somewhere here in the course or stockpile, and you're trying to control the bin level, which is a few minutes away from that process. So especially if you know some of these aspects that is going to complicate your control, and you involve metallurgists with that understanding into the design aspect, that means that actually you can interact at the earliest stages and trying to influence the design, which is going to help a lot to make it easier for process control later stages. The course is not only focused on comminution, we are covering the whole value chain. Thickness is another area that I have been working with them for a long time. And it's one of the area that actually normally is overlooked and people that don't pay attention a lot, but there are lots of issues around the control logic, addition of flocculant to the system, the sensors, they have lots of issues. And this is one of the examples, like we have the sensors, we have the measurements, and the people, they have been thinking they're adding flocculant to the thickness. So as you can see in the left-hand side, they're using the plastic pipes, and they're thinking that actually they're adding flocculant to the system. But when we tested, actually, because of these bends, nothing was been added. So by modification of the system, actually we solved the problem. The maintenance of the sensors are very important. Choosing the right sensors, that they are low maintenance, with lots of advances that is happening these years, it's very important as well. And we cover some of those aspects in our course as well. And one of the key points is the wrong installation of the sensors. The sensors, they need special requirements that people have to be aware. And often we found that actually sensors, they're not working very well because of the wrong installation. So in this case, like in the thickness, they installed an ultrasonic sensor to define the mud level, but because it was installed very close to the wall of the thickness, the sensor was giving the wrong reading. And then they moved into using the bare bottle to measure the level of the mud. And then by adjusting the installation, we managed to get that sensor to work. And this is, again, is another aspect that we are covering in our courses, to what are the requirements for installation of different sensors. And one of the things that I couldn't help myself to not to put it in is you shouldn't always trust to the drawings, especially the P&ID drawings, because there are lots of changes happening into the process that is not captured in drawings, and that affects your processing and your control logic. So in this particular case, you got a distributor that distributes the feed into 4 thickness, and this bypass that actually is bypassing the feed to the thickness on the floor is nowhere in the drawings. And that has a huge effect in the way that you're operating and you're controlling, but it's not basically properly captured. And some of those actually happens a lot. And just one last slide before I go to the course layout. As I mentioned, we know that actually there are lots of stuff in the advanced process control as well. And that's a topic in our next webinar that we basically going to come very soon around the advanced process control. And we're going to cover aspects around data analytics, benchmarking process control, and then how to design model predictive controls, touching on soft sensors, and also in advanced control around model-informed process control and role of AI and machine learning in process control. So these are some of the aspects that we're going to cover in our 4-day course, as well as in our next webinar. And if you're interested and you want to know more about the course, I would encourage you to visit SMI website. So we have the course detail up at the moment. We are looking to registration for the first course to be run in August. And I'll just put the layout of the 4-day course. The key point is, what we want to do is this course will be flexible for people that already have been involved in process control and they got a good understanding of the basics. If you want, you can actually just register for the day 3 and 4 and just touch on the advanced courses. And the people that they're interested to know the whole spectrum, you can actually apply for the a full 4-day course, which covers the basics as well as the advanced course as well. And that's it. I hope that actually you enjoyed the webinar, and I'm happy to get the comments and questions now.
All right, thank you very much, Mohsen. All right, I will take the questions and answers. Mohsen, what we'll do is I'll read through the question, and then if you can answer it. Our first question is there currently a control system that allows automatic mineral sampling in a conventional crushing circuit, for example, primary, secondary, without plant shutdowns?
Okay, so if I understood your question correctly, is it about, if it's about just taking a bulk sample for sizing or testing, there are basically sampling tools that actually they can take the belt cut sample as well, automatically without stopping the process. And I've seen many of them that actually they're running in operation, and they got different designs that, again, we cover those in our course as well. And then you got online size analyzing technique that there are plenty of different technologies that are out there that they do online size analysis as well. There are those techniques out there that you can do bulk sampling as well as online size measurements.
All right, thank you, Mohsen. That somebody has popped up their hand to answer a question.
Yeah.
What I'd appreciate is if you wouldn't mind just going to the Q&A button and just typing in your question there, and then I can pass on the questions to Mohsen that way. Mohsen, so far we haven't got any further questions, but I do know that often it's there's a little bit of a lag because people are busy typing in and they're coming through.
Yes.
So I thought what I would do is just pick up on the course that you're looking to run, and if you could just go through what is the process in terms of registering for that.
Yeah, so if I go back to my slide here, so I mean, if you search in SMI website, probably it's hard to remember this link, but if you type in smi.uq.edu.au, which is easy to remember, and then search for courses or online training courses, essentially you're going to go into the page that actually has whole heaps of other courses as well. We got lots of interesting courses, and then process control is one of them that now is open for looking into the details, as well as if you are interested, you can express your interest and register for that. Essentially, you can go to the SMI website and use that. As I mentioned, we made this course flexible because we know that actually there would be a wide range of people coming in. If you're already pretty much advanced in the basics and don't like to sit with the basics, you can just register for the day 3 and 4 and use that. And what we have done, actually, we used we got a special discount for the students. We know that actually financially, probably students are most vulnerable people. So we gave the 50% discount for the students if they want to apply. And also I asked to provide 2 free seats for the students, but for that you have to do a little bit of homework, which explained in the course page.
All right, thanks, Mohsen. I've got 2 questions. I'm going to do the one that's coming that's written, and then I'll try and open the line and see whether we can get Vahid to ask his question rather than type it. But yes. The first one I've got here is, what program or software do you currently use in machine learning?
I mean, we're using a wide range, so probably that's something that Pancho, Francisco, and Gordon can talk about that as well. But at the moment, we are using Python heavily in our work, and I know that most of the industry people actually they like that as well. I mean, in terms of the platform with Python, there are lots of different platforms that they support Python, and you can use that. And we are basically using that one as well as a primary package. Also, we are trying to use MATLAB in conjunction with MATLAB Simulink, because there are lots of good toolboxes in MATLAB for AI and machine learning that we can implement them, especially around the reinforced learning that we have been running. I know that Francisco has been using MATLAB Simulink, MATLAB toolbox in conjunction with Simulink for that purpose. But Python, I think, is the primary one that we use. But most of them, they're easy transferable.
All right, thanks, Mohsen. All right, Vahid, I'm going to open it now you to talk if you'd like to ask your question. I haven't done this before, so it's a good shot. So Vahid, I don't know if you would like to unmute yourself and ask your question.
Yeah, because you're muted, Vahid.
All right, Vahid, I don't know if you're with us, if you wouldn't mind just unmuting and ask your question. All right, I'm going to move on to the next question, and maybe we can come back and give that another try a little bit later. All right, another question here is, Mohsen, in your view, what is your view of missing input data for mineral processing control? For example, key data such as mill loads, feed size to different parts of the circuit.
Yeah, I think we can list a lot. So, and I think Malcolm agrees with me that actually we have a whole heaps of other measurements that actually we have in our mind. So for some of them, and that's one of the key objectives for us as well in our team, we are trying to identify, if you want to do effective process control, what are the key parameters that we need to measure that we are not currently measuring? In many cases, what we found is it's not really essentially about designing new sensors. It's more about maybe taking a different approach, like soft sensors. And that's what I've found over these past few years that actually is going to deliver a lot of value. Essentially, you're designing sensors, which is a model. It's not a physical sensor, which uses the input from different sensors that currently installed in the processing plant, and trying to infer parameters that you can, it's very hard to measure, or you cannot measure them reliably. And that could be a good input. Like one of the examples is our meal filling prediction tool, which essentially we use our power draw model and the meal load measurement model that basically we have, which uses the power draw measurement, which normally can be done reliably in operation plant, and the meal load measurements that's often done by load cell or basically the lubrication pressure, and then, or turning pressure, and then use that to infer the total filling and ball filling, which is very hard to measure. There are lots of hard sensors that over the past few years have been developed, and people, they install them on min shell and trying to measure. The feedback I got, it's around the trust to the numbers and maintenance of those sensors. But essentially, this could be one of the measurements that actually you can then use it into the process control. And I can name many other ones as well that actually you can use this kind of sensor approach. But I think another aspect which is important is to know what's the control logic that you want to do and how the reliability of the measurement that you have is going to impact the performance of the process control, and then come up with how you can improve that measurement, or what type of measurement actually gives you the best performance. But there are a lot, I think, in different aspects that you need to measure.
Right, Mohsen, here's an interesting question for you. Is it possible to implement part of AI and machine learning to optimize whole process from comminution until concentrate? If yes, how about human contribution to support when the model has been deployed?
Yeah, so I think this is, my answer would be too futuristic because we are a long way to get to that point. But my vision for the human contribution, if we have such a model running, would be actually a strategic thinker, because essentially those models, they're going to push the limits of your process, but still they would be constrained. And what happens is essentially what you have, and that's probably is the vision that I'm promoting, is you got this the stabilizing control that takes care of the stability of the process, and the AI and machine learning techniques, they're going to set the set point for the process and trying to push the limits. But where I'm thinking most probably you need the human contribution is to identifying when you're pushing the operation to the limit, where are the constraints now? And can we, essentially by readjusting the targets, remove those constraints and let the operation to re-optimize. So, I've been talking with my team about that one. So essentially what I'm thinking is maybe in the future, when you go to the control room, the operators in the control room would be the people that actually they are very good in strategic games, because essentially you can look into the whole processing plan as a game, and you can identify where are the constraints and where is the point that actually the whole system stuck and you cannot move them. And then think about what you can do to remove that constraint, which allows the AI and machine learning to push, again, the process to a higher limit. And to me, that would be the role of the human if such a thing is possible then.
All right, Mohsen. Here's a question that I think probably come up in your course, but let's see if you can do it in under 60 minutes in terms of an answer. So, do you know any application using real-time data information coupled to model predictive control in the minerals industry? And what do you think about this new approach for comminution?
So if that's like the conventional model predictive control that is in the market, so there are groups that actually they're doing that. But essentially what they have done is they developed, in many cases, they developed like a linear response range for different processes. And then they use the live data to inform those models and do the prediction. And there are different groups, and I've been interacting with sites that actually they implemented those ones as well. I mean, it showed that actually they had lots of advantages, but in my view, still there's a room for improvement of this approach by incorporating non-linear models. That's essentially a short answer if I want to do. But we capture some of those actually in our main course as well, yeah.
Yeah, and I suppose the question was, are you aware of any examples? And
yeah, I mean, there are many actually. I mean, like in Chile, there are lots of sites that they're using them. In Australia, there are many operations that they're using these ones. So I don't want to advertise for a specific group, but if you're interested, we are doing the same thing as well. So you can come to us.
Okay, fantastic. And all right, do you prefer to use just one term to control processes or more, and why?
I'm not sure if I get the question very correctly. What do you mean about one term?
I'm not 100% sure,
Yeah.
Mohsen. Maybe
if you can basically rephrase your question, because I'm not sure if I got your question correctly.
All right, maybe if we can have another go at that question, I'll come back to it. All right, here we go. For model-informed control, are current models suitable for online application?
Not all of them. And again, that's something that actually we try to move away from the traditional models that is designed for process design and optimization toward the models that actually they are more suitable for process control. But essentially, you can benefit a lot from the existing models. So I think the backbone of those models that we are going to design for process control would be the models that already developed and they're verified. But in many cases, it's more like a simplification and removing the need for calibration of the models or trying to infer those calibration factors from the processing data. So that's a move that actually needs to be done to be able to use those models.
All right, Mohsen, we've come to the end of the questions. And I know from the last couple of webinars, when I get to this point of thanking you for the talk, a couple more questions pop up. But we are busy bumping up against the end of our time slot. So I'd like to just thank you very, very much for your time and for your presentation. And I'm sure there are a number of people that are incredibly interested in participating in the course, and we look forward to their feedback. What I'd like to do now is just give you a bit of an update on what will be coming through next week's seminar. So next week we have Dr. Sarah Holcomb from the Center for Social Responsibility in Mining, and she'll be presenting on cultural heritage management in the resource sector, establishing good practice approaches. And then just a heads up that from the 16th of June, we'll be looking to move the lunchtime slot to a breakfast slot. And as discussed last week, we're going to be doing this so that we can make the time a little bit more convenient for our colleagues in Chile and in Canada. And then the other one which will come through in the webinar series later on is this year is the 50th anniversary of the JKMRC. And Professors Don McKee and Tim Napier-Munn have been working on a book to celebrate the 50th celebration. And I'll be hosting a couple of sort of fireside chats where we'll work our way through the different chapters and ask questions and remember the great people that have worked at the JKMRC and the work that they've done. So that's it for today. And I just thank you very much again to Mohsen, and thank you very much to everybody for phoning in. We have, as I said, received a question just out of time. So what we will do, if you wouldn't mind just dropping that in an email to Mohsen, I'm sure he'll be more than happy to respond to your question. But yes, thank you very much, everybody, and look forward to seeing you this time next week for Sarah Holcomb's talk and then after that we'll be moving to a morning slot. Thank you very much.
Thanks,
Goodbye,
everyone. Bye-bye.